was the one that talked about writing a self-unquoter for a total functional programming language. In that case, it was systemf and systemf omega. And what made that particularly exciting was the fact that there was a folklore conjecture that writing such a thing is impossible. And we've seen how the folklore proof was wrong, and there was a nice constructive proof that it can be done because they actually gave a representation and they gave the unquoter. So first of all, quick show of hands. So who attended my presentation last year? Okay, so about half. Okay, it's okay. So the first couple slides, I'm going to set the scene so that we are all on the same page. So this is the part that I would have skipped if it turned out that everyone was here. And oh, one more thing. So if this was like a proper scientific presentation, I would give the result and then we would see how we get there, but I want to keep the suspense a bit up. So first a couple of terms that I'm going to be throwing around. When I say data, I'm going to mean something that is in normal form. A quotation is going to mean an injective and total mapping of terms to data. So the idea behind the quotation is that if you have some language, so this is always going to be with regards to a concrete language. So you have some language, you have terms of that language, and we want to represent every term as a different term which is in normal form, right? So if you have two terms which reduce to the same thing, they still need to be two different representations. Because the point is that we want to represent the expressions themselves. And because of this mapping, this quotation, is not going to be a function defined in the language. So it's not going to be a definition that you can write out inside the language, because inside the language you can't really see the difference between two terms if they reduce to the same thing. But the whole point of a quotation is that it needs to be intentional. And then shallow versus deep representation. So shallow representation, in here I'm going to mean representation that only supports one operation, so it's geared towards a single operation that we want to do over the terms, whereas a deep one is one where I can choose the operation after I have already constructed my representation. And the related concept is embedding, but the big difference is that here we are only interested in situations where the terms are in normal form. So this was actually theoretically much more important last year, because if we don't care about our representation being data, then of course it's trivial to self-represent any language, because I can just take any term and say that it represents itself, right? So to summarize, a quotation mapping, and I'm going to use this marking for that, something that given a term, closed term E, it will give us a term of some type exp, where exp is some type family which is indexed by the type of the term that we are quoting.
So do I understand it correctly that the columns are in the same type theory?
Yes. So yes. So
columns,
this
right?
mapping is not in the language, but E and quotation of E are both in the same language. Yes, or at least they are in this setting, because that's what we are going to be looking at. Of course, in different settings you can. So there are meaningful things you can talk about if they're in different languages. But here we're interested in self-representation. And then, so there are two basic things we might want to do with an expression that, with the representation of a term in the same language. Two interesting things. One is to unquote it. So an unquoter is a function which is written in the language. It's a normal definition of a normal function in the language, which, given a quoted term, gives us it reduces eventually to the same term that we originally quoted. So the type of this in a typed language would be exp a to a. And then a reducer is a function also defined in the language. So it's just a normal function defined in the language, which if E has the normal form V, or it reduces to V, then this reduce of the quotation of E reduces to the quotation of V, right? So just a quick example to make sure that we're all on the same page. So suppose that we have a language where we have natural numbers and addition and strings. In that case, these are 4 different terms, right? These are all separate terms. So 3 plus 5 is the term that's made up of adding 2 numbers. And 8 is a term which is made up of just 1 number. And of course, this term reduces to this one. This term, of course, doesn't reduce to this one. And then so suppose that we use strings as our quotation, as a representation of terms. So then the string 3 plus 5, which represents the term 3 plus 5, if I have an unquoter, it means that it will reduce to the term 3 plus 5. Whereas if I have a reducer, it means reduce of 3 plus 5 will reduce to the string representation of the normal form of this. Okay, so last year we talked about unquoters, right? We talked about making a function for a total language which can go from this description of a term into the term itself. And now in the follow-up page, and of course the result was that it is indeed possible to do that for a total language. And then now we're looking at this situation. So what are the languages that we are going to look at? Just a bit of lambda calculi. So we have the untyped lambda calculus, which I hope everyone is familiar with. We have lambda abstractions and applications. And it's not a total language, of course. We can easily come up with terms that don't have normal form. And the self-interpreter is not really interesting because, well, it's going to be partial anyway, and it's not hard to make something with... So, yeah, it's not an interesting problem. It's been done to death. And then we have the simply typed lambda calculus, where we add types to lambda abstractions. There. And the types that we have are just function types. Now, of course, in any practical, like you can't really do anything with it because you don't really have any types. The types are not well founded. So you need to add some base types. And once you do that, you add some extra constructors types there. But there's no type level abstractions. There's no polymorphism. So how would you even type? Like, never mind implementing it, but what would even be the type of the reducer or the unquoter function, right? Because we said that, reducer goes from xpay to xpay such that the result is in normal form. But, you can't type, the type for all a xpay to xpay is not expressible in a non-polymorphic language. Now, when I was making these slides, this was like in January or something, but 2 weeks ago I was at the formal structures of computation and deduction conference, something like that. And in one of the workshops there was a talk on system N, which is a supposed monomorphic lambda calculus. So it's not polymorphic, but it has slightly richer types than STLC. And they say that the conjecture is that it's actually equal in expressive power to system F. So I don't know what that means. I have no intuition for it. But I'm just saying that this last sentence, now I'm less sure of it, because if there is a monomorphic lambda calculus, and if you can do the same self-unquoting thing that the paper from last year did, which you should be able to do if they are really equivalent. But I don't know. I have no intuition on this. I just wanted to mention this because, maybe I'm very wrong on that point. And then we have system F, where the big thing is that we add polymorphism. So now we have for all types, but we still only have a single kind of star, which means that we don't have type constructors yet. We only have atomic types and type variables. And then, of course, because we have for all types, we need to have a matching instantiation thing. So we have type instantiation and we have type abstraction, which one of them introduces and the other one eliminates for all types. So this only has parametric polymorphism, and yes, this can be self-unquoted. So this is what I talked about last year. And then system F omega is the last one we are going to care about today. So this is a lambda calculus where we have kinds which are richer than just star, meaning we have type constructors, like type transformers, right? Because we can have type level lambdas and we have type level application. And we can self-unquote it again as we saw last year. So now we're going to look at the typed self-evaluation. So from now on, we're not going to care about unquoting, we're going to care about reducing. And we will start with a much simpler problem, which is to just evaluate the simply typed lambda calculus in Haskell. So here, right, we have the host language is Haskell. And when I say Haskell, as we will see, I mean Haskell plus a lot of GHC language extensions. And then the target language is very simple. It's just simply typed lambda calculus. So, one thing we could do is to just start writing it out longhand. We have a data type for terms in a given context. And hopefully there is no surprise here to any working Haskell programmer. We use a GADT so that we can restrict the type of the term that we are representing. So like a lambda abstraction will represent a term with a function type, and so on. And then we use a type level context to track the type of the variables in scope. So the problem, and then we would need to write the actual interpreter in terms of this data type. So the problem with this is writing this is actually needlessly complicated, because then we need to implement our own substitution. And the end goal of all this is to write something that we can write in the same language that we are interpreting. So we want to keep the interpreter simple, and we want to keep keep making the language that we interpret richer. So because of this, a much nicer way of doing it is to use a higher order abstract syntax for the representation, because this way we basically import the meta-level notion of functions and function application into our interpreter. So we get that for free as long as the language that we will try to push down into still has functions. But if we start with the simply typed lambda calculus and we're only going to make that richer, we're not going to get rid of functions, right? So the function arrow is going to be one of those things that we can always count on. So here in this representation, we completely get rid of variables. And instead we say that when we have a lambda abstraction, we represent it as a function from term representations to term representations. And then we can write the evaluator for it very easily, because here, this is where the magic is. Here we use the concept of functions in the Haskell functions, or the meta-level functions, here to just apply this on the representation that we apply it onto, right? So this is like a very neat, very small STLC interpreter. Turns out it's not really written in Haskell, it's actually written in Haskell plus GADTs, right? So the language that we are, like the host language, it's actually quite rich. So what we have here is that we have very small code implementing an evaluator for a very simple language, but it's written itself in a very complex and very rich language. So what we have here, right, is that we have simply typed lambda calculus that we are interpreting, and then we have the host language, which is Haskell with JDTs. And somewhere in between, we have the line of totality, so everything below will be a total language, and everything above is a partial language. So the program from now on, for the rest of the talk, is just going to be pushing down that and lifting this up. So first, let's do some pushing down. Let's simplify the Haskell program. And when I say simplify, I mean the program is going to get more complicated for humans to read, but it's going to be simpler in terms of what are the language features that it uses. So first of all, let's get rid of the GADTs. So what is the GADT, right? A GADT is simply a type where the type of the result is restricted in some way. So if we have, now of course this is it, so if we had the single GADT, so the idea for the first step is we still have GADTs, but we only have one. We take that, the existence of this particular GADT as an axiom, right? This is basically just a reification of what's in Haskell plus extensions is written as the tilde character, right? So we say that if two types A and B are equal, then the witness of that is this constructor called refl. Because if we have this, then all the GADTs can be rewritten to be completely parametric in all their type parameters, and the constructors will contain a proof that they are not just any random type. So to give you an example, when we do a lambda abstraction, right, we say that here is the actual content of it, right? So it's a function from a representation of a term to representation of a term. And this will have type t because we are parametric now. But we also store a proof that t is equal to t1 to t2, where I'd also like to stress that t1 and t2 are existentially bound in this constructor. Right? So even though our end result is an exp of t, there exists t1 and t2 such that t has this form. And similarly, when we do application, we don't need to restrict the t, but we still need an existential for the intermediate type, the type of the argument, which of course has to match the type of the left side of the arrow of the function. Yes?
That's a universal.
Well, that's because Haskell's syntax for existentials is a bit screwed up. So,
okay, sorry.
So this is the Haskell syntax for an existentially bound. Yes, it really is. Like if you think about it, if you write this, what this means is that for any t1 and t2, the constructor abs has this type. Which means when you are given a constructor of abs, t1 and t2 are existentially bound because they were chosen by your enemy when he was constructing. Yeah. Okay. So this is just confusing Haskell syntax, but this is still Haskell. So we are still in Haskell, but now we don't have GADTs anymore. So what do we need of refl? Because if you want to get rid of GADTs and we want to say that okay, we only suppose the existence of this single GADT, then of course we can't start pattern matching on the refl in our code and then do stuff with it, because then we are still using the full power of GADTs. So we will see what is the theory of type level equality that we need. What describes refl type? So, well, first of all, it's reflexive, symmetric, and transitive. So it's an equivalence relation. It's a congruence over type constructors. So, if t1 is equal to t2, then f of t1 is equal to f of t2. It supports coercion, of course, because if A and B are the same type and I have a value of type A, then of course I can go to B. And the arrow function, the arrow type constructors, the type constructor for the function space, is injective on both sides, right? So these are properties that are easily provable in Haskell, in real Haskell with real GADTs, because we just keep pattern matching on the constructor of this, which would be refl, and then the unification will make everything equal in just the right way, but the definition is also going to be just refl.
So are you here talking about some total subset of Haskell, or?
No.
Because everything is provable in Haskell, in that sense.
Okay, so for here we're talking about like fairyland Haskell, where yes, you can suppose that it's total in the sense that so the point here is that later on we're not going to write these functions. We're going to see if we just have them as axioms and we suppose that they are correct and sound and blah, 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 then we can just use them.
Mm-hmm.
So yes, but of course, so Haskell is not total. I mean, your whole interpreter function could just return undefined and be done with it, right? But in some sense, that's not what we're interested in. So then, if we have this, we can of course rewrite our code, the one that just used pattern matching on GADTs. So now we can just pattern match on normal constructors, but then we get the equality proof in scope, and then we can use the combinators from the previous slide to basically what we want to arrive at is to turn this f, which has just type x t0 to t1 or something. Once we are given an argument, we want to turn it into something which, where the argument type matches the lambda abstractions type. And so all this is just the longhand form of what GHC gave us for free when we just pattern matched on the GADT constructors, because then it's able to prove that f and f prime are the same thing, but here we have to make sure that we do all the conversions by using type equalities. Because of course, otherwise everything is just parametric, right? So we are given, and we have all these existentials in scope that we can't unify with each other, but with the equations we can. So what's left? Well, we have recursive types, right, in our representation. So let's get rid of those next. So we use the standard. So this is very standard technique. We add a single isorecursive type constructor mu, and we factor out the recursion. So instead of exp using exp, we add an extra type parameter f, and then everything is in terms of f, and then we tie the knot. And the reason that I use it here at kind star to star, so the reason that we have this extra type parameter here is simply because that's the only kind we are going to need later on. So we could do it without the A, and we could generalize it to any kind, but we don't need to, simply put. So to keep things simple, we're just going to use this definition. And then, because of course here we have a single type parameter, which is the type of the term that we are representing. So this will be the A, and xf will be the f, right? So if we do that, the only difference with the previous slide is that we have f here. So we factored out the recursion, and then we take the fixed point of this. So this is not really an interesting change, but it means that we don't need a generic way of making recursive types. So what's next? Well, types as such, or rather data types and existentials. So now we're taking bigger steps. Now we are making some progress because we can use the standard Scott encoding of data types and data type data constructors to turn them into something that takes destructors that correspond to the constructor cases, and a constructor is simply choosing the right destructor, as we will see in the next slide in an example. So the idea here is that given some continuation type, if I have a function of this type, so this is a type that consumes the equality proof and the body of the lambda abstraction will give me the continuation. And if I have another function, which given a pair of a function term and a argument term will give me the continuation, then I can give you the continuation, right? The only way to give a value of this type is to apply either this or this on either these or these, right? Are we clear on this? Okay, and we got rid of the existentials as well, with the usual trick of turning them into rank 2 universals, because now the existentials are just parameters to the destructors. So the destructor has to be ready to accept any choice of T1 and T2 in this example, which means that, so this here now is a real universal quantifier, but they are at rank 2, of course, because this whole thing is like, this whole thing is a function, and the first two parameters, the two parameters to it will need to be polymorphic functions. So we've gained, so we've lost data types. We gained not having data types, and we gained not having existentials, but we had to give something in return, which is higher rank, or at least rank 2 universals. But given that we're marching towards system F, or F omega or something, it's not going to be a problem. So so just to give you an example of what exactly this Scott encoding means. So how do I recover the constructors? Well, the constructor for app is something which, given the two destructors, will given the two destructors, we choose the second one, the one that corresponds to the application, function application case, and lambda abstraction is one that, given the same two destructors, will choose the first one, right? So the only different, like the matching itself simply happens in these two lambdas both of them taking two arguments, and both of them using a different one out of those two, right? And then matching is even simpler, because when you want to match, you just so here we have a nice way of doing this, because here we take the fixed point thing, right? So here we take an xt, not an xft. So this is the thing that already has the knot tied, and we give it functions which again work on tied versions of the type. But then it's just a matter of folding and unfolding at just the right places, and we just pass it the two handlers for the two possible cases. So okay, so if we put it all together and we go back to our evaluator, this is the version we have now. So this part hasn't changed, right? Because this is just handling the type level equalities that we used to implement GADTs. The difference here is that instead of having like host level pattern matching, we simply have host level function application. Right here we apply. Here we use these two functions. So if E1 prime is a function application, then we do this. If it's a lambda abstraction, then we do this, right? So it's the exact same code as before. All the pattern matches have turned into lambdas, and the parameters to the lambdas are exactly the fields of the constructors that we have encoded. So where are we now? So now we have our mini Haskell, right? In some sense it's smaller, and in some sense it's still more complex than Haskell, because we don't have data types anymore, but we do have rank 2 types. We don't have recursive types, but we have this single explicit type former for isorecursive types, this mu type level fixed point combinator. and we have the single GADT for the type level equalities. So yeah, so the progress we made so far is pushing down the host language. Yes, and now we're going to make further progress towards the language that they in the paper call system f omega mu I, and we will see what the mu and the I stands for. So first of all, what can we do about those pesky type equalities, right? So as I said, EQ is still a GADT, and to implement this theory, we needed to use GADT pattern matching. So instead, we can reduce everything that EQ gives us into just Leibniz equality. So we can say that the important thing about EQ is if A and B are equal, it just means that any f of A can be turned into an f of B regardless of the choice of f, right? That's what it means for two things to be equal, that I can replace one with the other in any possible context. Maybe I shouldn't be talking about this is what equality means if I'm in a room with several homotopy type theory and cubical type theory people, but yeah. So if we have this, we can recover the definitions of raffle, seam, trans that we had before, and course as well. Of course is really simple, right? Because if we said that for any choice of f, we can go from FA to FB, well, I'm just going to use the identity. So this is type level lambda x star x, and apply the equality on that, which exactly means that it will be a way to go from A to B. Yeah, and all the rest we can just write. Except, we had two combinators which said that the arrow, so the function type constructor, is injective in both arguments. The problem with that one is, this is an intensional type function, right? So we have to look at the structure of the type to be able to take it apart into the left-hand side and the right-hand side, and then to show that I can replace one or I can replace the other. So this, we need to add some explicit support. So if you want to get rid, so the point here, right, is that you want to get rid of GADTs completely. You want to only pass around, these Leibniz-style equality witnesses. So it turns out that then we need to add some extra support into our language. And what we do is some kind of type level, type inspection thing, right? So basically we want something which is similar to how in Haskell with type families, right? You can have type family instances which do pattern matching on the structure of the type. So to support that, we will add a type level type case. So we don't need, so this is type level, right? So if R is a type of kind star to star to star, then type case R and function type will be a type of kind star. So we add it to the language. This is like a keyword, right? It's bold and uppercase. That should show you that it's a keyword. So the idea is that if this is not a function type, this would just get stuck. We will simply arrange so that it's never used unless it's a function type. Because, of course, all these... So remember that the quotation mapping, it's an external thing. It's not a function of our language. So when we make that quotation mapping, we will simply be careful not to put any of this type, unless we know by inspecting the term that we are building a representation for that this will be a function type. So if we have this, then it's easy to... Oh, and so the idea is that this, if it is a function type, it reduces to this type constructor applied on the two types. So this gives you a way of taking it apart and then doing whatever you want with it. So this allows us to recover left-hand side and right-hand side injectivity basically in the left-hand side case, basically because we say that the type which, given a function from t1 to t, type from t1 to t2, will simply give us t1, right? This I get the same result if I apply it to a1 to a2 or b1 to b2, right? Because that's what the equality gives us. So, and of course, if you want to use the right-hand injectivity, we just return beta here. Okay, so this should enable us to get rid of REFL, right? And that's the I. So in system f omega mu I, the I stands for intentional type case. The case for function types is not going to be the only case, as we will see. But for now, everything we talked so far, just functions are enough. Okay, so what about isorecursive mu types? Basically, the authors of the paper say, just add it. Don't care, keep it. So we simply add to our language. Yes.
But then, are we not going to be not total? I mean,
so
if you just add isorecursive mu types, then it's a partial language.
Yes. So if we go back to this one, right? So if we do this, we're going to push this down to here, which is what will be in a later slide. Yes, that's correct. Okay, I might as well spoil the whole thing, right? Instead of making the jump from here to here, instead you're going to push this up to here and meet on this side. So that's the sad part of this paper, right? Unlike last year's paper, where we were in this side, here we lift this, push this down, and stay here. I'm sorry. Yeah, 37 minutes in. If you only go out now, I totally understand. But it's still interesting because so unlike the paper from last year, and I see that Balázs is not here, right? But he was laughing at the construction that we actually used in System F to prove that it can do self-unquoting because it feels like a cheap trick, right? Here, this is not a cheap trick. We really are just taking a normal, like an interpreter that a human would write to do meaningful interpretation, and we're just simplifying away all the details until it becomes simple enough that the extra features of the language compared to the simply typed lambda calculus is not hard to put in and support. So this paper is more like a software engineering result, if you will. Whereas last year's paper was really just, we can do this trick and it works out, and even though it doesn't, it's not what you want to do, but you can't deny that it's a data embedding or data representation of system F and system F omega in itself. The F omega, okay, so in last year's paper, the F omega one is more real, like it's more substantial, right? But the system F one is really just a cheap trick. It's really to settle the question of, can we do typed self-unquoting in a total language? Yes, we can, here it is. And it's not good for anything, but it proves that it can be done. So this is different. This is really about doing this in the natural way. So so we just add fold and unfold to get to introduce a mu and to get rid of it. And just to spell it out for those in the audience who might not have picked on what you said, of course, you might ask the natural question that, okay, it's one thing to have type level recursion, but don't we also need value level recursion because we want to walk or traverse these terms, right? And if the term itself is represented as a recursive type, surely I will need value level recursion to traverse them. But it turns out that once we have type level recursion, we have value level or term level recursion as well, because we can do this trick of of defining a generic fixed point combinator. So this is on the term level, right? Because it takes any term of type A to A and gives you its fixed point. And R is not a recursive definition. Diag is not a recursive definition, but of course it uses fold. Fix is not a recursive definition, but of course it uses diag and unfold. But yet, at the end, we arrived at fixed point combinator. So for the rest of the paper, they just simply use recursive definitions because they already have the machinery once you have mu types. By the way, this was so. I couldn't really find an example of like the smallest way of doing term level recursion once you have type level recursion. So I had to like load it into the turn of the termination checker and play around until I was able to make the whole thing. Because it's just tricky. It's easy to get it wrong. Okay, so what we arrive at is system f omega mu I in all its glory. So we see on the type level we added mu, and we added type case, and then on the term level we added a fold and unfold to introduce and to eliminate mu types. Of course, it's still polymorphic at any rank. So the fact that we needed rank 2 types to encode existentials is not really a problem in this language because we can use types at any rank. Just like in system f omega, we have type constructors, blah blah blah. We have isorecursive types and we have intensional type case, but it's only at the type level. So there's no runtime type information thing going on here, right? There's no, like these type cases, they don't introduce some weird value level, proof relevant something yet. Okay, so putting it all together, the interpreter for simple lambda calculus in this language, it's basically exactly the same as it was in the previous slide when we have removed enough of Haskell. So the representation is exactly the same. We use, of course, mu here. And then, and I haven't even written out the interpreter because the interpreter is exactly the same. You just have to fold and unfold at the right point, but you can't even mess it up because it will just not type check otherwise. And of course here, right? No, actually not here. Sorry. I don't have that here. Okay, I have that on a later slide. I hope so. Where okay. So in the interpreter, right, we used RL and RR, so the injectivity of the function type constructor. So that one now simply becomes using using the same definition, but the definition uses type case internally. So that's why the interpreter would look exactly the same as before. The type case is only needed so that we can define RL and RR. Okay, and then we switch to a parametric higher order abstract syntax simply because for some processing, so for some intentional processing, it's useful to be able to have variables. So these are meta variables. These are not the variables of the language that we are interpreting. These are useful, for example, if you want to like compute something like this, the depth of a term, right? Because then we hit an abstraction and we need to pass it something of the right type before we can continue, because otherwise it doesn't give us access to the body of the lambda abstraction, right? So for purely pragmatic reasons, and because we can, so it doesn't really mess up the interpreter, we add one more constructor for these meta variables. And then, of course, a meta-closed expression is something which doesn't have any variables. So for any choice of v, it has x type xv, which means that it can't possibly have any. Yes.
Where does alpha come from?
that should be a T. Sorry.
Okay.
Yeah, it should be a T. So these are typed meta variables. Yeah. But this alpha here is also just, yeah. Okay, so this is the one that you were asking about. So yes, we are indeed on this side of the division between totality and partiality. So this is the language we are in now. And now the next step is to write an interpreter in F omega in F omega mu I. Right? So we just add two new constructors. We add the constructor for type abstractions and a constructor for type application or instantiation. And there, the idea is that this is all and this push and this inst, these are, so I'm not going to go into the details of them, but they're basically type families which, so this one is a witness that T is a for all type, right? Because if you have a type abstraction, the resulting type, so the type of the term that you're describing has to be a for all type. So we can't just use a equality here, because of course there's not a single concrete type that we want to restrict it to, but it has to be a polymorphic type. And this one here, maybe I just and this one here basically is to say that we have, so it's an f of type t, but in t we have some new type variable which we can use. And inst is also, inst is a witness that t is an instantiation of t0. So you can get t by taking t0 and putting in, sorry, by taking t0, and the type that is the type of the full term is an instantiation of t0, which is a for all type. So to implement these, again, we need to be able to look at for all types and take them apart. So this being system f omega, we don't have kind polymorphism. So it's always a concrete kind we have here. And what we do is we give you two customization points, if you will. One is on the outside and one is on the inside. So if you have a for all type and you apply type case on it, then we push one in and we apply one on the outside. And this is enough to express these predicates, so is all and inst, and it's enough to implement push, which is a way, which, like I said, is a way of saying that recurs into something where we have this extra type variable. But again, I realize that the details are a bit light on this in my talk, but these these are implementation details, because basically, if I just write them out, they are just huge type families. But internally, they are eventually come down to various applications of type case. And similarly, there's also, and this is actually a trick that they did in last year's paper as well, to also implement this strip all and under all type families, which are used when, so suppose you have a term and you're writing a traversal which is not an interpreter, right? Because the whole point of a deep embedding is that you can choose, or a deep representation is that you can choose what you do with it afterwards. If you are writing something which will interpret it, then you want to care about the for alls, right? But if you're writing something which, for example, gives you the size or the depth of a term, then you don't want to care about the for alls. In fact, it becomes very cumbersome that the types will force you to, instead of getting a number from the recurrence side, which you get simply because of this, right? If you get something of like for all A net, that's not what you want. You just want the net. You don't. I mean, you know it's just a net. If something has type for all A net, it's the same as a net, and you want to get rid of that because you just want to like add one to it if you want to compute the size. So this is what strip all is, because some traversals are completely monomorphic. They don't care about the type of the term that you're traversing, but the representation is typed. And because of that, the traversal is typed because the traversal is driven by the constructors, which are actually destructors. So you can't recurse at any different type. You have to, you just have to recurse using those those destructors that you can pass to the constructors, right? So you need some extra like magic to be able to get rid of them. Okay, so where does this leave us? So the next step we want to do is self-reduction, right? So far we have arrived here, right? If we add the handling of polymorphic types, terms of polymorphic types. And so now for self-reduction, we just add more constructors to represent the constructs of f omega mu I. So first of all, because we have a new type former, we add the new type case branch. So if you have a mu ft, and then you apply this type case on it, you get fix of ft. So again, you take apart the two types that mu is applied on, and both are passed to fix to do with it as it feels. And we add new constructors for fold and unfold, which are the two new term formers. And they have a witness that the type is a mu type, or they have a witness that the type is a type applied to a mu type, right? No surprises here. And again, to handle these equations, or to be able to do something with this, that's where you will use the new branches of type case. And so and there we have it. So like I said, the end result is a bit sad. It would be much nicer to arrive somewhere here, but we don't. So, well, maybe it's good news because it means that there's still future research to be done in this area. But at least this shows a very nicely principled way of making a self-evaluator by getting rid of all the features that we can, choosing the core set of features that we are confident that we will not lose, right? And then, making a bit of a leap. And maybe we could have been smarter at the last step. So, sorry, I thought you. Okay. And that's basically it.
Yeah. Okay. So there is a talk next year about that.
Well, we'll see, right? We'll see what they are up to next year.
Did they try to make it total, or did they elaborate on why this does not work in a total setting?
So so in a total setting, the big question is what kind of representation do you use that you don't need mu types, but you can still do so the evaluation itself is inherently recursive, right? So you need some way of recursing, but you would want to do it in such a way that it doesn't introduce a generic fixed point combinator. And they couldn't come up with one, I guess. So like I said, this feels very different from the paper from last year. This is really just software engineering, and so we're gonna need recursion, so we will have recursion. Yeah.
And did they prove that they actually define an evaluator?
Yes.
Yeah. And
Yeah, because that's also part of the problem, right? So last year, the fact that unquote had type xt to t was its own proof.
Yes.
But of course, in a partial language where every type is inhabited, yeah, just having a function from xt to xt is not a big deal.
You had a remark in the beginning that, I don't know what it was exactly, that if the language is expressive enough, then the problem is trivial. Isn't it the case here? So like a self-reducer, is it easy to define in the untyped lambda calculus?
Self-reduce should be easy,
Yeah.
yeah.
So,
Yeah.
okay. So now it's a bit more, it's more complicated because
Well, of course,
everything needs to be well typed.
Yeah, exactly. So at least it's type preserving.
It's type preserving, so that's the only thing that.
Yes. So if yes.
And maybe they prove something about semantics as well, like the operational semantics of the untyped thing works the same as the evaluation, or something like this. No? Do they have something like this?
No. So So you could say that. Yeah, how is GHC not the same? GHCI rather, right? Because GHCI interprets a partial language, which is Haskell plus a lot of extensions, and it's written in Haskell plus the same extensions. So, and it's the same situation. But of course, it's not typed. So the contribution here is that it's typed. So the type should give you at least some confidence that it's not doing something totally wrong. So at least it's not an implementation of GHCI where everything just reduces to unit.
Yeah, but I mean, sure it's typed, but they entirely skipped out the interesting part of an implementation, which is the handling of functions and closures, because they just use the function space.
Yes, but that you will always have. I mean, even if you implemented a simply typed lambda calculus self-reducer, you would still have functions. So that's the only thing you can count on if you have any lambda calculus, that you will have lambdas and function application.
But I mean, you don't necessarily need to have an interpreter which uses like this higher order thing. So you can also write an interpreter which uses just closures.
Right,
but maybe not a well-typed interpreter.
But
certainly for dependent types you can't write a well-typed interpreter without a higher order.
So the problem then, of course, is that you're pushing this language upwards instead of downwards if you do that, because then you need a host language which is expressive enough that you can write your own substitution and engine in that language. So here we were trying to make big strides towards a small language that we have a reasonable chance of implementing ourselves. So it simply saves a lot of work not having to figure out what is the kernel of those operations that we need in addition, so that we can keep writing this substitution engine in the target language. Yep.
If we just had type case but not iso-recursive types, do we know whether it would be total or not? Are there any results about that?
Well, that's a very good question. So, like I said, in the quotation mapping, they arrange such that all the type cases are always, they're always at the right time, so they never get stuck. But I don't know whether you can guarantee that, because then you still have a.
But if it gets stuck at the type level, then
Yes.
Then you neutral term, it's fine.
yeah, but I think it's totally if we have a total type case function, because that's something which can be modeled in a dependent type theory with codes for types quite easily.
Yeah, I mean, I guess you could just add one more one more parameter to type case, which it would return like the fall through case, right? And then like make it total by construction.
No, that would just be a new neutral term. You have type case, you also have neutral term for type case being applied on a type variable. It's fine. So that's the only case that you cannot reduce, right?
Well, currently, if you apply it on... Oh, right, yes, no, I see what you mean, yeah, because there's no other type.
Well, now there's mu, and maybe mu comes, but if we don't have
Yeah, but if
mu,
you don't
then
have...
it's-
Yeah.
Yeah, so sorry, the pizza arrived. Let's talk about the other questions by the pizza and leave some stuff for the next presentation. Thank you for coming. And